Okay, hi guys. Me. Yep. Good afternoon, everyone. Okay. Let me remind before we get started. Let me remind you guys that assignment 1 is due today. So notes. Assignment number 1 due today. Okay. And I think it's too soon for assignment 2. But as soon as I can put up some of the material on assignment 2, then I'll also post assignment 2. So let me just say assignment 2 should be posted by Friday. And it'll just be due like next week, Friday or something like that. And assignment 2 is going to be on the material that we're going to start today. That is like the second section of the notes. It's about relations. Assignment 2 is on relations. Okay. Oh, I have posted these recordings to YouTube. I've posted them in 2 different playlists. One playlist is, one playlist is for lectures. The other playlist is just for like tutorials. The difference is, I guess, the tutorials will have like, if we did more examples and assignment questions and stuff like that, then that will be posted in the tutorial. Oh, my video is not good. Okay, that's better. Okay. And the links for those would be in my e-learning. Okay. Let's see. So today, like what we want to start looking at are relations. So right, in order to define what a relation is, we need to have a notion of an ordered pair. Okay. So we need to talk about ordered pairs in Cartesian products. We do have unordered pairs. Okay, so let's start by remembering what that is. So remember the axiom of pairing, which says that A and B be sets. Okay, there exists set C such that X is in C if and only if X equals A or B. And this allows you to construct the unordered pair of A and B, right? So once you have that axiom, we have this set. This is the unordered pair. Of A and B. And all we want to do is figure out a way to have an ordered pair. Like we need a way to make this the first thing instead of just one of the things, right? So a set doesn't, like this set can't do that for us. Remember, a set only knows its elements. So it only knows that A is an element and B is an element. A set can't tell us which is the first one. Remember, because this set is the same as this set. Both these sets have the same elements. So there's no first or second thing. There's just A and B, and they're both in there. Okay. Okay. So the first option, well, one of many options. So we need an ordered pair I guess I can use A, B. And the ordered pair of A and B we need this. We need it to satisfy the property that two ordered pairs are equal if and only if and only if the first coordinates are the same and the second coordinates are also the same. Okay. That's what we need right now. Because after this, we need to start talking about relations. Relations are just sets of ordered pairs, so we need ordered pairs. Okay. Okay, so one option, like we've seen before, we can just make up an axiom. We could say you can make up an axiom called the axiom of ordered pairing. Let's call this option A. Do the axiom of ordered pairing. And it would be like something like there exists that A and B be sets, then there exists just a set or an object AB such that, you know, if it's equal to another ordered pair, that's true if and only if A equals A prime and B equals B prime. Okay, that's one option. This is not the option we take, but that would be fine. Okay, the option we take is we're going to construct construct AB which satisfies this property. Let's call it property star. And we're going to need from given axioms. Okay. The reason why we take option B is because we're going to make the order pair of A and B a set, and this is set theory. So in another class, we would probably take option A and it would be fine. Okay, but we're in set theory. We're doing everything from sets. In particular, this ordered pair is going to be a set. Okay, and how we construct it is just with a trick. Okay. I don't remember who came up with this trick. Maybe yeah, I don't want to, I'm not sure, I don't want to guess. Okay, but we have a definition. Right. Let A and B be sets. Okay. Then define the ordered pair of A and B. Well, we need it to be a set. So actually, let's see, what should we do? This is going to be a set with two elements. And the first element is going to be just a set A. I used lowercase, sorry. Yeah, okay. Sorry about that. We're going to do this. Okay, it's kind of seems like nonsense. Okay. So what we need to do is first we need to prove that this is a set from our axioms. Then we need to prove that it does what we want it to do. Okay, and what we want it to do is have a first element and second element. Okay. We have this proposition. Let A and B be sets. Then the ordered pair of A and B is a set. Okay, that's the first thing. Now, if AB equals A prime B prime, or I should say AB equals A prime B prime if and only if A equals A prime and B equals B prime. That's our proposition. And this is the second property. That's what we want ordered pairs to do. We want them to have a first thing and a second thing. And two ordered pairs are the same if they have the same first coordinate and the same second coordinate. If they have different second coordinates, they're different, you know, that kind of thing. Okay. So let us prove that the ordered pair is a set. Okay. First of all, A, B, and A, these are both sets by axiom of pairing. These are both unordered pairs. This is the unordered pair of A and B. This is the unordered pair of A with A, which is just has one element. Okay, and now the ordered pair AB is just defined to be the unordered pair of this with this. Okay. This is a set by axiom of pairing. Okay, that's the proof of the first part. Okay, so fine, we've constructed a set, but it's kind of useless unless it does the second thing. You know, I can construct all kinds of crazy sets. They're not all useful, you know. We need this one to do something. We needed to do this. We needed to have a first thing and a second thing. It's not immediately clear that this should work, but at least I see, like, when I look at this set, I do see a way to distinguish A from B. You know, A is an element of both of the elements, and B is only in one. So there's a way to tell the difference between A and B. Okay, so now let's try and establish 2. Okay. Okay. Suppose A equals A prime and B equals B prime. Well, in this case, it's not to see that both of the ordered pairs are the same, because all the I know that A and A prime are the same, and I know that B and B prime are the same. So I can just replace all the A's with A primes and all the B's with B primes. Oops, this should be an A. Sorry about that. This should be an A prime. Okay, and this is just A comma B, A prime, B prime. Okay, so if A is the same as A prime, B is the same as B prime, then the two ordered pairs are the same. That's kind of what you would call the easy part of the proof. Well, I guess not easy, but the short part of the proof anyways. Now we need to show, our goal is to show that if AB equals A prime, B prime, then A equals A prime and B equals B prime. Okay. And so we have to compare, given that we know that this set is the same as this set, we have to find a way to compare A and B and A prime and B prime. Sorry, to compare A and A prime and a way to compare B and B prime. Okay. So one way to do it is to split it up into cases. Case 1 is that A is equal to B. Then the definition of the ordered pair looks like this. That's the definition. Okay, the unordered pair of A with A is just A. Okay, so this first thing is just a singleton, same as the second thing. Okay, so this is a set whose only element is this singleton of A. So we have this. Okay. And our hypothesis says that AB is A prime B prime. So in this case, we have that AB is this set, and A prime B prime is this set. Oops, this is an A prime. Okay. So this is our hypothesis here. Okay. Now for this set to be equal to this set, it means that both these sets have exactly the same elements. This set on the left only has one element, has the element the singleton of A, and on the right we have possibly two elements. Okay. But both of these elements have to be equal to this element. Okay. Sorry. Oh, I see someone. Okay. Okay, now, again, now we do the same kind of thing. On the left, we have a set with one element. And on the right, we see a set, there's two things, A prime and B prime. Well, they both have to be the same as this one element, right? So this tells us that A equals A prime and also A equals B prime. And if this set had more and more elements, they would all be the same as A. That's what it means for two sets to be equal, they have the same elements. Okay, and now we can stop because we've shown that A equals A prime and B prime equals A, but A is, we're assuming that A equals B, so B prime equals B. Okay. So if AB equals A prime B prime and A equals B, then we've shown that A equals A prime and B equals B prime. Okay, so that's the first case done. Case two, that would be the case that A is not equal to B. Okay, again, what's our hypothesis? We're assuming that this equals this other set. Okay. Okay, so what does our hypothesis say? A is not equal to B. Well, under this case, that tells us that the unordered pair AB is not the same as the unordered pair of A. Right? Since B is not equal to A, this set doesn't have the same elements as this set. Okay. Okay, so now take this unordered pair. It's an element in the right-hand side. Okay, so either it's an element of this set, it's either equal to this set or the other set. Okay, but if it's equal to this set with one element, then these two elements are equal to each other, which we assume is not true. Okay, so we can eliminate this. This is not true since A is not equal to B. Okay, so we have that AB equals A prime B prime. Okay. And now we do the same thing, but with the singleton A. Take the singleton, it's in the right-hand side. Okay, so I shouldn't say we have the singleton of A is in the set, it's either equal to this or this. If A equals A prime B prime, well, we've shown that A prime B prime is equal to AB. This is a contradiction because we've already shown that these two things, A and or unordered pair of A and B, are different. Okay, this is a contradiction. Okay, well, it has to be one of these two elements, so we must have that A equals the singleton of A equals the singleton of A prime. Now these two sets have the same elements. All that means is that A is equal to A prime. Okay. And now we can use this fact. Then B is in A prime B prime, which means either B equals A prime or B equals B prime. Okay. If B equals B prime, we're done. We've shown that A equals A prime and B equals B prime. Okay. If B equals A prime, then we just use the fact that A equals A prime to show that A equals B. So if B equals A prime, then B equals A prime equals A contradiction. Because this whole time we're in the case that A and B are different. Okay. So if B equals A prime, we get a contradiction. Therefore, it must be that B equals B prime. And so A equals A prime, B equals B prime as required. And that ends the proof. Okay, so we've shown that this, honestly, this technical way of defining the ordered pair of A and B, that it does the thing we want, which is to distinguish the first element from, like, the first entry from the second entry. Okay. Oh yeah, just a quick note. So in about 5 minutes, I'll stop this meeting and then just restart. Oh, there's a question. Yes, please. Go ahead.
Hi, sir. I was wondering if for this course, if the proofs are more flexible, because I was looking at how you prove this, and it is like you follow a method, but like with the assignment, I couldn't think of like a way to prove it exactly. So like I was wondering if the proofs are more flexible in this course, or is there like one right way to prove it or stuff like that?
Um, I would say there's not just one right way to prove it. Um, to say more than that, I'll just have to take a look at how the first assignment goes. And I think I'll have a better idea of how to respond after that. Is that okay? Yeah, okay. Um, yeah. Okay. So I was just before that, so that was a good question. Yeah, okay, but before that I was just saying how um I'm just gonna restart the meeting in about 5 minutes so that it doesn't cut us off in the middle of something. Okay, so yeah. Anyways, okay, so we have our ordered pair of A and B. That's good. Okay. Okay, so now we just make our definition. And this is a very general and abstract definition. Okay, we'll say that a set R is called a binary relation if every element of R is an ordered pair. Okay. That's called a, then if all the elements of R are ordered pairs, then we have a binary relation. Okay. And being a binary, like lots of things are binary relations, you know. Okay, examples. Oops. Everything has to be an unordered or an ordered pair, not an unordered pair. Here's one. Okay. More. We'll have R cross R, which is the set of all A and B, such that A and B are real numbers. Okay. We have the divides. This is supposed to be the divide symbol. That's going to be all the integers. All the integers such that B equals AM for some M. We have less than or equal to, maybe that's going to be the set of all real numbers, such that A is less than or equal to B. Okay. Some more examples. We have the set of X and A such that X is in some set X, and A is a subset of X, and X is in A. Okay. And we could call that X membership in X, membership relation. Okay. So there's a lot of different ways to relate things to other things. Okay. So this notion of relation is very relaxed. And you'll notice like this chapter is just about there's a lot of definitions. And the reason for that is there's a lot of different relations that are useful in math. Okay. Now I'm going to end the meeting for everyone and just restart it with the same link. Okay, does that make sense to everyone? Just rejoin the same meeting. Okay.